right, this is our next reaction for February 20th, 2025. This is the acid-catalyzed hydration of an alkyne. And this is going to be similar to our acid-catalyzed hydration of an alkene, except we're going to end up with a different outcome in terms of the reaction. So the overall reaction that we're going to have here would be something like an alkyne like this. Now, it could be any R group over here on the right, but I noticed that I did choose a terminal alkyne, and there's a reason for that. You could use an internal alkyne with this one as well, but here I'm choosing to use a terminal one so that we see the difference in regiochemistry for this one. Here you would of course use water because we're doing a hydration, but you would also need a strong acid. One that is particularly utilized is going to be triflic acid. Okay, so that'll be HOTF, with the OTF being the triflate. This is a very, very strong acid. The pKa for this is around -13, which means that it's even stronger than hydrochloric acid, which has a pKa of around -7 or so. Of course, what that means we're going to have here is that the triflic acid, since it is so strong, is going to protonate the water. And so when we draw our mechanism, we're going to start out with H3O plus as our active acidic species. And it turns out that it will initially do a Markovnikov addition. So this will be Markovnikov, just like what we looked at before. And so when that happens, it will add the OH over here to the more substituted side, and that will leave us with a double bond here. However, this is something called an enol. Notice that there's an alkene and there's an alcohol, and they're right next to each other. They're attached to the same carbon. So this is called an enol, and this is going to be thermodynamically unstable. And this is going to undergo something called keto-enol tautomerization, which is something that is in the organic book in chapter 7 in the Cardi book that we utilize. And so you can go and take a look at that at this point, since we are going to utilize it. I will go through the steps of that and how that looks in this mechanism right now. But what's going to effectively happen is, and the H that's on the alcohol here gets removed, and an H gets added to this vinylic carbon atom here. And then instead of the double bond being between the two carbon atoms, we end up with the double bond between the two oxygen atoms. So this ends up tautomerizing, which is where we move around atoms, generally protons or hydrogen atoms, to form a constitutional isomer of a structure. So initially we're going to get this, but then in the end what we're going to get is this. So this is the keto form, and the transition between these two is what's called keto-enol tautomerization. Okay, so when we draw this, this is the product we're gonna end up drawing, is the ketone. Now, for myself personally, I almost always draw the enol initially, and then, I don't necessarily need to go through the mechanism, but then I draw the ketone out after that, just to make sure I'm getting the structure correct, because it would be really easy to make a mistake in doing this. The particular keto enol tautomerization we're going to do today is going to be acid catalyzed, because we do have the acid present. We do need the strong acid, triflic acid, to make this work. The addition to the alkyne is going to be a little more difficult. So, all right. So let's go through the mechanism of this. So this will start out in the same way that our other Markovnikov additions have started out. We're going to first do an electrophilic addition, followed by coordination, and then we're going to undergo that keto enol tautomerization. So let's draw out the substrate that we have today. If it helps, you can draw on the C's to keep track of everything. And we're going to first do that electrophilic addition. We're going to grab a proton. So we had one hydrogen atom here, and now we have a new hydrogen atom here. If you want to do this in color to keep track of the new atoms, you can. This would be the more stable carbocation. We are going to add, just like we have done before with the alkenes, the proton to the less substituted side so that the carbocation can be on the more substituted side. And now we do have water present, and so we're going to utilize that water as the nucleophile at this point. All right, and we're going to attack there, so that'll be our coordination. Okay, so we notice here, of course, we still have a positive charge, or we do have a positive charge on this intermediate. And so we need to get rid of one of these protons. So another molecule of water would come along and take that proton. So that'll be, I suppose I've added a proton transfer in here in this mechanism. So then we're going to have that proton transfer. That's going to give us an H3O plus, which is what we started with. And then we will have our final enol form. Okay, well, not our final enol form, but we'll have our enol form. And then this is going to undergo the tautomerization. Okay, so what I'm about to draw is still part of the mechanism, but it is kind of an additional step here that's going to be really the keto enol tautomerization mechanism that's going to get us to our final product. Let me clean this structure up just a little bit here. All right, so again, this is going to be acid catalyzed, and with the end goal in mind is that we basically need to add a hydrogen atom to the carbon atom here, and then we're going to need to take away this hydrogen atom. So we know already there's going to be a bit of proton shuffling. So when we have an acidic environment, so this is going to be an acid catalyzed keto enol tautomerization. So this is going to attack here, and this is going to be effectively another electrophilic addition step. So when that happens, we'll end up with 3 hydrogen atoms over here on the right side. And we still have our OH here, and we now have a positive charge here. So this should look pretty familiar to kind of what we were doing in the last reaction. Now, here we see we have a positive charge next to an atom with a lone pair. So this is a positive charge or electron deficiency next to a lone pair. And that's a setup, that's one of our setups for resonance structures. So I'm going to take this down here, and I'm going to draw the resonance structures, or the other resonance structure. Okay, so now we have the positive charge on the oxygen, which always feels a little uncomfortable. But if we think about the stability here, that carbon up here, which did have a positive charge and did not meet the octet, now meets the octet. So that's going to be favorable. Also, if we notice what this looks like, this basically looks like our ketone product, except that we have a proton still here. So that's going to be the last step of our keto-enol tautomerization, is that we're going to do a proton transfer to remove that. Okay, and there we have our final ketone product. So whenever you're doing these, you're just going to want to go ahead and, if you're asked to do the mechanism, obviously you're going to need to go through the mechanism. So just a reminder that it's the electrophilic addition followed by coordination, just like our other Markovnikov additions. And then because the nucleophile was neutral here, we do need to do that proton transfer in the last step. And then we do the keto-enol tautomerization, which is effectively a combination of electrophilic addition, followed by technically drawing the resonance structures and then doing a proton transfer. Okay, I'm going to do a couple more examples just to show you what the products look like and maybe a little more possibilities or a few other possibilities related to the regiochemistry or the kind of constitutional isomers that can occur with this. So here's another example. Okay, so here again, this is going to do that Markovnikov addition. Followed by the keto-enol tautomerization. So what I'm going to first draw is the product of the Markovnikov addition. Okay, which if we're looking at this, we've got 1, 2, 3 carbon atoms. 1, 2, 3 carbon atoms. So we see that's in the right place. We know that this doesn't last long, so I'm going to put a bracket around it. And effectively what's going to happen here is that that proton gets taken away, a proton gets added out here to that, and then we put the double bond here. And so when we do that, that's going to be our final product for that particular reaction. Okay, so far I've done a couple of terminal ones. Let's look at what happens when we have an internal one and some of the possibilities that can occur there. Okay, so here we can realize that we have the possibility of the OH being added on the right or on the left, right? But we realize that both sides have this ethyl group, and so in the end, it turns out that it doesn't really matter which one of those is what actually happens. So we can draw both out, but hopefully we're going to quickly see that we end up with the same product either way. Okay, So let me just double check. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 carbon atoms. There's the enol form. If we added to the other side, one, two, three, four, five, six. And then if we take both of those to the keto form, again, we're going to get rid of that hydrogen atom. We're going to convert the bond in the middle to a single bond. And then we're going to add the double bond there. If we look at this, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, with the ketone at the 3 position. So we would give these two compounds the same name, and therefore they're the same molecule. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, so here we're only going to get one product with the symmetric alkene. Alkyne, excuse me. And then when we have the terminal alkyne, we only got one product. However, if we have an internal alkyne that's asymmetric, we're going to get 2 possible products. So let's look at an example like that. Okay, let's say this is our substrate. Again, we're going to use triflic acid and water. So here we have the possibility of the hydroxyl adding on the left. And then I also have the possibility of the hydroxyl adding on the right. All right, so those are 2 distinct enols. They're different from each other. We would give them different names regardless of the stereochemistry. So now I'm going to do the keto enol tautomerization, and notice this is really convenient and easy to do on, you know, this white pad work or this iPad where I can erase things, but also on a whiteboard. It's really easy to do this to where, you know, you're not having to draw out every single step of the mechanism. Okay, so if I'm naming this over here on the left, 1, 2, 3, 4, 5, 1, 2, 3, so this would be pentan 1, 2, 3, pentan 3-one. Or if we were doing functional class naming, it would be diethyl ketone. Some of you may have had this one for your unknown in the unknown identification product. 1, 2, 3, 4, 5. So this would be pentan 2-one, or MNOP, methyl propyl ketone. Some of you may have had that as your unknown. So both of these would be products. They would be, you know, easily formed, both of them. One of them may be more, you know, thermodynamically stable than another. You might get more of one than the other. That's something we would have to either look up, or you'd have to do an experiment to determine which was which. So if we see here with the asymmetric alkyne that we're going to get 2 products, 2 distinct products. All right, and that's all we have for Markovnikov addition of water to alkynes. So we're going to get a ketone when we do this reaction.